Good morning. It's so weird. So I only see you guys today and then I don't see you until next Tuesday. How weird is that, right? So remember, no classes on Thursday and Friday. No classes Thursday because it's Remembrance Day, Thursday and Friday. How about a sad face? You'll survive, I think. Just a heads up, right? So I won't see you until Tuesday next week. So that feels weird. I posted an assignment. So I posted assignment 8. And it will be due on Sunday. Okay, it's just 4 questions. So and it's just on 1 sample proportions, and we've moved on to 2 sample proportions. So I'll get you assignment 9 posted as well. But it won't be due on Sunday, but the assignment 8 is due on Sunday. November 14th. At, of course, 11:59. And I'll say, I'm pretty sure it's only 4 questions. Okay. Kind of doesn't look like a Y there. Okay, so that's just a heads up. Okay. What else did I want to talk about? Okay. I'm sure you've noticed. Let's see here. Dashboard. I posted, so I did put the date quite a ways back for test 1 or test 2. It's going to be on November 23rd. But we do also have kind of a pile up here. So I'm kind of running a little bit behind schedule. It's okay. It's okay. I knew this was going to happen. So the chapter 9 was kind of in an ideal world. Usually we don't get that far, so it's okay. But whatever we get to on, and I'll screenshot this here so we have it. Save. Right, and so here, let me bring it in and we'll crop this up here. Sure. Right, so we've got test number 2, but really it's going to cover test number 2 will cover all the material up to and including November 19th. We'll cover material from test, or so from the day after test 1. So when was that? Oh, I'm pretending I'm on Moodle. Test 1, so Thursday the 21st. From October 21st to November 19th. Okay, so we'll see where we get to. I don't think that we're going to get through all of chapter 7. It'll probably be just part of chapter 7 because things are kind of piling up there. I keep bumping it forward, but yeah, so we'll see. But while I kind of am doing administrative stuff, we're going to finish 2 sample proportions today. And so 6.2 is 2 sample proportions. So that's what I want to wrap up completely today and really have a solid 2 sample proportion day. And then for next week, read 6.3 and 6.4 And maybe I should put it in kind of read 6.3 and 6.4, of course, in the textbook. Don't know why I felt I had to say that, but I did. Read 6.3 and 6.4 in the textbook for next Tuesday. And I'll say before class next Tuesday. Oops. Okay. It introduces chi-squares, and it follows kind of the same idea, the same rhythm for hypothesis testing, and we're going to focus on hypothesis testing for chi-squareds. But I want you to have read it, so when I say it, it's not the first time you're seeing it. It's hopefully, you know, the second time, or potentially even the third time if you've read it twice. I know, I'm dreaming. Read 2 sections twice, Emily, really? I know, weird, right? So let's see here. So I feel like there's something else that I'm forgetting, but can't think of anything. In terms of review, we introduced 2 sample proportions, right? So we introduced 2 sample proportions. And we talked about the assumptions. We started with the assumptions for the confidence interval. So if we're making a confidence interval, then we need to check certain assumptions. But then what we kind of left off at, I'm pretty sure, is if we're doing a hypothesis test, we check slightly different conditions. Okay, and so we introduced 2 sample proportions, and the conditions we need to check. Okay, and what we said was we still need to check the same conditions that we did in the 1 sample case for independence. So I tend to break up the conditions into independence and normality. Okay, and so it just helps me remember what I need to check. Okay, and so if it helps, then you can break it up that way too. If it doesn't help, then I don't know, don't do it. So the independence condition is the same for hypothesis testing and confidence intervals. Okay, so this condition or these conditions we have to check regardless of what we're about to do. Okay, so we have to check that each sample, because now we have 2 samples, right? And so with 2 samples, right, we have an N1 and an N2. We have maybe X1 or X2. We have P1 hat and P2 hat, right? And so now each sample has some information, right? And so we need to check the conditions on each of those samples. And so each sample was randomly selected, right? And that's to ensure independence. So each sample was randomly selected. Right, that's one thing we have to check. Usually it says, but if it doesn't, you have to say, we assume that each sample was randomly selected. Okay. The samples are independent of each other. Okay, so sample 1 is independent of sample 2. That's new. the samples new in terms of when we compare it to the one sample case, because then we only have one sample and it's independent of nothing, right? Because we're not comparing it to anything, and so that doesn't apply. So the samples are independent of each other. And then I'm going to call this one optional because it's a little bit excessive, but sometimes we'll also want to check that the sample size, if you have a huge sample size, you want to check to make sure that it's less than 10% of the population, right? And the idea being, okay, good, it's good to have a huge sample size. So that's a good thing. It gives us more robust estimates, right? But we want to be careful, because if you've collected too much of the population, you're going to be introducing observations that are not independent of each other, right? And so N1 is less than 10% of population 1, and N2 is less than 10% of population 2. That one's optional, so we can talk about that one, or you can skip it if you want to. I'll include it just for kind of completeness, but you can skip it if you want to. So now we went on to say, okay, we have to check the normality condition, and this is for a confidence interval. The normality condition, if we're doing a confidence interval, we talked about it. We said that we need to check that N1 times P1 hat has to be greater than or equal to 10, right? Or X1 has to be greater than or equal to 10. Notice that X1, if you have it, the number of successes, right? Then you can just use that. Here, this is just meant to help you find X1, right? And we need to check that N1 times Q1 hat is more than 10, or that N1 minus X1 is more than 10, right? That's the number of failures. Yeah. And we also have to check that N2 times P2 hat is greater than or equal to 10, or X2 is greater than or equal to 10. Same symmetry here, right? And N2 times Q2 hat is greater than or equal to 10, or N2 minus X2 greater than or equal to 10, right? These are the expected number of successes and failures, or sorry, it's the observed number. Yeah. Go ahead, Emily, flub it up when you're trying to emphasize something. It's the observed number of successes and failures, right? Oh, they did an update, and now I can't see the page breaks very well. So that's not really going to look good when I save it as a PDF. How about I move it to one page there? And while I'm at it, how about I give myself some more room here on the side? So these are the observed number of successes and failures in each group must be more than 10. Right, that's the same condition that we've been checking, but now we have to check it for both samples. So that's where we left off in our review, but that's where I also want to pick up for the conditions, the normality conditions for the confidence interval, right? And so now for the new stuff, to check normality. But now for a hypothesis test, so this is new since last day. So that was kind of I hope this one's not confusing. Here, I'll just say end of review. Right. But I wanted to review that really thoroughly because it's going to be really important that we have a good handle on checking the assumptions. Okay, so to check the normality condition for a hypothesis test, what we need is we use the pooled proportion. Now, we haven't really talked about the pooled proportion, but you basically put all your successes into a pool and take all your both your sample sizes, and then you find this pooled proportion. That's different from when we had to check it for a hypothesis test for one sample proportion, right? And so it's slightly different because in the one sample proportion case, we had to check against the null value, right? The hypothesized proportion, but now the hypothesized proportion is 0, so that's not really going to work for us, right? Or the difference in proportions is 0. So if we're doing a hypothesis test, then to check the normality, we have to have we first need to find the pooled proportion. So the pooled proportion is going to be denoted by a p hat. Now, that's different from the one sample proportion because it'll be obvious that this is going to be a 2 sample proportion question, right? And so then the p hat is denoting the pooled proportion. So p hat is denoting the pooled proportion. And it's going to be the number of, or the total number of successes, divided by the total of the sample sizes. Total of the sample sizes. Which is the same, so it depends on how you want to think about this, but you just have to pick one of the calculations, of course, and then they're all going to be the same. So depending on what information you have, right, one might be easier than the other. So if you have the number of successes, right, 43 out of 76 people said this, then you have the number of successes, 43, right? So then you can use x1 plus x2 divided by n1 plus n2. That's fine. If you don't have the number of successes, remember how you have to find it. It's n1 times p1 hat, right? Which is the same thing as n1 times p1 hat plus n2 times p2 hat. Oops, make that look like a 2 divided by n1 plus n2. Okay. So depending on what information you have, right, one might be easier than the other. So these are the same. Pick depending on what information you have. Okay. So, and maybe I'll bump that up here. There. Okay. So then once you have your pooled proportion, then you're going to check the assumptions for normality with the pooled proportion. Okay. So then check the conditions with the pooled proportion. Oops. So n1 times p hat has to be greater than or equal to 10, and n1 times Q hat has to be greater than or equal to 10. And let me see here. N2 times P hat has to be greater than or equal to 10, and N2 times Q hat has to be greater than or equal to 10. Notice, so here, sample 1 and sample 2. So you still have to check both sample sizes with that pooled proportion. Okay. And so here, notice that these are the pooled proportions. And remember, I don't think I need to say it anymore because I've said it so often and there's notes everywhere about it. But I also know that, you know, you're going to be in a panic at some point, and recall that Q hat is 1 minus P hat. All right. So make that a little bit cleaner. Once you've checked these conditions, and I just want to show you that there is a summary because I posted. So in part 2, now we're talking about 2 sample proportions, and here there's a summary of all the assumptions that we have to check, right? And I've got the 10% condition in there just for completeness. I didn't note that it was optional because at the time it wasn't optional, but now we're pretending it's optional. That's okay. And so here it breaks it up for if you're doing a hypothesis test or a confidence interval. So if you want to have it nice and compact, it's there on page 11 of that handout that I posted. Okay, so let's have a look at the formula sheet that I've posted. Okay. So on the formula sheet, now this isn't the one that you have to use. You can make your own formula sheet, but it's always nice to have a little bit of a guide and something that's already been made up for you, I think. So this is the one that I would have given you. Okay. And even though we're doing a hypothesis test for the difference in the proportions, right, which is what we're going to do, and then we're going to build a confidence interval for the difference in the proportions, I tend to use the hypothesis that, right, P1 is equal to P2, because I'm going to assume that they're the same until I have proof otherwise, right, until I have proof that they're not. Okay, and so, or equivalently, I'll say H naught is that P1 minus P2 is equal to 0, right? For me, if I have to check a one-sided test, it makes it really difficult. Two-sided P1 minus P2 is not equal to 0. That's easy enough. But if I wanted, for some reason, to show that P1 is less than P2, then I would have to say, okay, well, if P1 is smaller than P2, then that's going to give me a negative number. So then it would be less than 0, right? And that just is a lot more thinking than I want to be doing. And so I prefer to have them wrapped around the equality, but it really doesn't matter. Okay. In terms of the test statistic, because we knew that was coming, right? If we're doing a hypothesis test, we're going to state the hypotheses, we're going to calculate the test statistic, we're going to find the p-value, and then we're going to state our conclusion, right? And so that's kind of old news now, and now we just apply it. And so now you're going to be asking questions like, what's the hypothesis that I'm testing? Okay, and what's my test statistic? And then once you know what those are, then you can just kind of take it from there. And the steps are always the same. Okay, and so here I'm going to say we assume P1 and P2 are the same until we have proof otherwise. Okay. Remember when we use a Z-score, we typically subtract. So we have our estimate. So this is our point estimate, P1 hat minus P2 hat. That's our best guess at what P1 minus P2 is for the population, right? Seems reasonable, right? We have estimates for those, so we're just going to use those. Technically, what's happening here is you have minus, you have minus P1 minus P2, but since we assume that the null hypothesis is true always, so depending on which one you prefer, you're still going to see that P1 minus P2 is equal to 0. So we don't even include it in our formula anymore because it's always going to be 0, right? You could test that it's something other than 0, but you would need to read up on that because the techniques are just slightly different, but it's okay. We are not going to do that. Okay, and so the null hypothesis says that P1 minus P2 is equal to 0, right? So same idea, we always assume the null hypothesis is true. And I also have where P hat is the pooled proportion, just to remind you that you have to use the pooled proportions. And I've got the formula for the pooled proportion there. So let's talk about the Z formula. So we've got our point estimate for the difference in the proportions, fine, minus the null value, which is 0, okay? And then we've got this standard error, which now is using the pooled proportion, P hat, Q hat, which is 1 minus P hat, and then times 1 over N1 plus 1 over N2. That's a little bit nicer looking than the standard error for the confidence interval, right? Just depends on what you prefer. But so depending on which scenario you're in, right, that's going to determine how you find your standard error. Okay, so for the steps for hypothesis testing, so for a 2-sample proportion question, the steps for hypothesis testing are as follows. The steps for hypothesis testing are as follows. And I am assuming assumptions have been checked. Assuming assumptions, conditions maybe, assuming conditions, but we usually call them assumptions. Assumptions have been checked. Okay, so that's assuming that everything's checked out, and that's going to be your first step, is just check the assumptions. They're all going to pan out, and then you can do the test. So step 1 is to state the hypotheses. The hypothesis is always going to be, the null hypothesis is always going to be that P1 equals P2, or if you prefer, P1 minus P2 equals 0. If you like to see that 0, you can. Okay, and so the null hypothesis is always going to be that P1 is equal to P2, or same idea, P1 minus P2 is equal to 0. If P1 is equal to P2, but you're actually interested in the difference between the two, then of course the difference is 0, right? 2. And then the alternative hypothesis is going to be that P1 is not equal to P2. That's for a two-sided test, and that's the default, right? But you can test to see if P1 is less than P2 or if P2 is less than P1 by changing that, that sign, but the default is a two-sided test. So, or HA is that P1 minus P2 is not equal to 0. Right, so the two-sided test is the default, but could be less than or greater than, depending on the question. So then it would be a one-sided test. Maybe I'll put a little hyphen there. Okay. So that's going to be how you set up your null and alternative hypothesis. Now, one thing that I do want to say here is that it's going to be really important that you have question-specific subscripts, okay? Because otherwise, if you're just using generic P1 and P2, but you're comparing, you know, apples and pears, then how am I supposed to know which one is which? So at some point, you need to either define group 1 and group 2, or you can use question-specific subscripts. Okay. So note, we need, and I'll even highlight that, we need to use question-specific subscripts because otherwise our statement, it's not going to make sense, right? Such as P women is equal to P men, right? If discussing men and women. Oh, it's all no better. Oh, well. Right, for example, and maybe I should say that, not just period, for example. Or define group 1 and group 2 before using them. You don't believe that? I guess we'll find out. Or define group 1 and group 2 before using 1 and 2 as your subscripts, before using 1 and 2 as your subscripts. Okay. Okay. So you've got two options and they're all pretty, you know, reasonable. You have to be able to understand what it is you're talking about. So step 2 is to do the test, which is really calculate the test statistic. Calculate the test statistic. And in this case, doing the test, it's a Z test, we call it, because we're calculating a Z score. So Z is P1 hat minus P2 hat. Technically, minus, and I'll say minus P1 minus P2, but this is equal to 0 from H naught. right? Because we assume that H naught is true. So that's always the case. So we can actually just ignore it. Divided by the square root of P hat Q hat times 1 over N1 plus 1 over N2, I think. Let me just confirm. Yeah. Where P hat here is the pooled proportion. You would have calculated it already because you had to use it to check the assumptions. So you'd already have it, and so then you can just use it. Right, and then because we calculate a z-score here, then we use the z-table to find the area under the curve. So remember the p-value, so step 3, find the p-value. Find the p-value. Okay. Or I guess I was calling it gather evidence, but in a hypothesis testing scenario, I just say find the p-value because that's what we're doing. And so finding the p-value, if you have a z-score, that's going to be just finding the area in the tails, right, from that z-score. And so Z, of course, is centered on 0, and you're going to have some calculated Z. I'm going to do the negative absolute value of Z calculated. Oops. And the positive value of the absolute value. Because the Z that you calculate here could be positive or negative, but I just want to highlight that you just look at the area and the tails for both of these, right? So where Z calc is the Z you calculated, pretty basic subscript here, where Z calc is the Z you calculated in step 2. And then you find the area in the tails, and so these together make your two-sided p-values. Whoa. Two-sided p-value. You really just need to find the area in one of the tails, right? And then just multiply it by 2. Okay. For a two-sided p-value, this is the same as the one sample proportion, right? Once we have a Z, then finding the p-value is the same, right? It doesn't matter. So for a two-sided p-value, we find the area in one of the tails. In one of the tails and multiply it by 2. Multiply it by 2, right? If you're doing a two-sided test, then, a one-sided test, so if P1 is less than P2, for example, or if P1 is greater than P2, right? If that's your alternative hypothesis, then you only need the one side, right? Then you're only concerned with one extreme. The downside that we talked about was, okay, well, we don't really want to do one-sided tests because if we ever were to find something interesting on the other side, we'd have to ignore it, right? And so then it doesn't matter. And so you don't want to close that door. And so that's why we typically just do two-sided tests. But sometimes for practice, we'll do some one-sided tests. So I want you to be prepared for both, but in real life, you should just be doing two-sided tests, so not equal to in the alternative hypothesis. So, but for one-sided tests, you only need to find the area in the one tail. In the one tail. Okay, so for example, if your alternative hypothesis is that P1 is less than P2, right, then P1 minus P2 is less than 0. And so then you would be down here on the negative end, right? So then the alternative hypothesis is that P1 minus P2 is less than 0, which means that your Z would be down here, and this would be your one-sided p-value. And I should say Z calc because it's going to be negative, right? Whereas if you were checking the alternative hypothesis that P1 is greater than P2, then really what you're checking is, or I'll say, or P1 minus P2 is greater than 0, then you're going to have a difference that's greater than 0. So your Z calculated is going to be positive here. So then this is your one-sided p-value. Okay, once you have your p-value, your conclusions stay the same. Okay, so let's see here. Step 3, step 4. Conclusion. The conclusion stays the same, right? Once we have our p-value, the conclusion that we make is never going to change, right? If the p-value is small enough, you have enough evidence to reject H naught. And if it's not, then you don't have enough evidence to reject H naught. So if the p-value is less than the alpha level, we have enough evidence to reject H naught. Okay. And then, of course, we have to state the conclusion in terms of the question. State what that means in terms of the question. Okay, so here's option number 1 and option number 2. So if the p-value is not less than the alpha level, right, or you could say it's greater than, then I'm just going to copy this because it's the exact same. If the p-value is greater than the alpha level, notice that when it's equal to, it's never going to be equal to, so we don't really need to worry about that, but that's going to be a judgment call. There is no kind of, yeah, if the p is low, then the null hypothesis must go, right? So if the p-value is greater than the alpha level, we do not have enough evidence to reject H naught. So then we state what that means in terms of the question. But these are the same as the conclusion rules, let's say. I'll say from before. So that's the beauty with hypothesis testing, is it is really long and complicated and there's a lot of ins and outs, but once you have it under control, then you can really tackle any type of hypothesis test, right? As long as you know what the null hypothesis is, because then you can just negate it and make the alternative hypothesis. And you need to know what the test statistic is. And then we can just kind of go from there, right? And how do you find the p-value if it's a different test statistic than a z-score, right? We're going to see some different test statistics, and I'm going to show you the different ways, but usually you can just use software, right, to find those p-values. So even for z-scores, should probably just use software, but we've got the z tables, so why not use them? Okay, so what I want to do is I want to do a question, and it's the question at the very bottom. And it's going to be a hypothesis test as well as a confidence interval. So we're really going to practice checking the assumptions, checking all the assumptions, and doing all of the confidence interval, hypothesis testing, all that fun stuff. So here's the one that we're going to use for practice. So a surprising number of young adults, and now that I'm reading this, I feel like there's a typo in here somewhere. Can't wait to find it. A surprising number of young adults ages 19 to 25 still live in their parents' home. A random sample by the National Institute of Health included 2,253 men and 2,629 women in this age group. The survey found that 986 of the men and 923 of the women lived with their parents. Okay, and so part A is just to get us warmed up. How large is the difference between the proportions of young men and young women who live with their parents? Okay, so we'll start there. And then part B, is there evidence that there's a significant difference in the proportion of men who live in their parents' home compared to women? Okay, that's a full-on hypothesis test, because is there evidence, right? So that's what makes this a hypothesis test. Okay. It looks like a tiny question, and then you read it. Oh, is there evidence? Oh, a full-blown hypothesis test. Right, and then of course, construct a 90% confidence interval. So I can't do an exclamation mark. It's not that surprising. It says make a confidence interval. So that's just a confidence interval, right? But we need to be able to look at these questions and determine, am I doing a hypothesis test or am I doing a confidence interval? Or in this case, I'm doing both. So I need to check the assumptions for both. Okay. So here we're going to say that since it asks for a hypothesis test as well as a confidence interval, we start by checking all the assumptions, right? And so it's going to save you a lot of time if you just read the entire question and figure out, am I doing a hypothesis test, or am I doing a confidence interval, or am I doing both? Because then I may as well check all those assumptions at the same time, right? So since it asks for a hypothesis test as well as a confidence interval, we will check all the assumptions at the same time. Okay. So before I even start with this question, because I want to get it over with, and hopefully that's what you do as well, right? You want to make sure that you check the assumptions, you don't want to forget. But then once you've checked them, you can kind of forget about them. And so for the assumptions, right, we check independence, First thing we check is, were the samples randomly selected? Okay, so a random sample by the National Institute of Health seems reasonable that they actually did collect a random sample. And so the sample was randomly selected. And then we found that there were this many men and this many women. So it's implied that both of those samples were randomly selected. Okay. And so the samples were randomly selected. So that's good. The samples, if we're just selecting a random sample and it happens to include this many men and this many women, then we can assume that those two groups are independent of each other. There's no reason to think that those are dependent of each other in any way, right? And so we're just looking at the same age group. And so we usually say something like, it's reasonable to assume that the samples are independent of each other. It is reasonable to assume the samples are independent of each other. Yeah, so then it would have said that, right? If they were randomly selected in a certain place, then they would only be representative of that place. But it doesn't say, it just says a random sample by the National Institute of Health. So I think we're safe. Otherwise, yeah, there would be issues there, but not really, because then you can only talk about that one sorority house. So it defines the population that you're able to talk about. So it's reasonable to assume that the samples are independent of each other, and you just want to argue that they're independent of each other. And also the optional one, oops. It's reasonable to assume that sample sizes of 2253 men and 2629 women in this age group is less than 10% of the National Institute of Health. Implies that it's national, probably in the States, because I've never heard of the National Institute of Health, but so it's reasonable to assume that that's less than 10% of young men and young women. So this one's optional, right? But if you want to have kind of the full-fledged answer, then we would say something like, it is reasonable to assume that 2253 is less than 10% of all young adult males and 2629 is less than 10% of all young adults females. Okay, make that look like females. Okay, that's the independence condition. And maybe I'll remove this here and just kind of highlight it like that. Otherwise it's like colon, weird. So that's the independence condition. Now we're going to check normality. And because I know that I have to do a confidence interval and a hypothesis test, I'm going to do them at the same time. So the normality condition, oops. For a hypothesis test, First, I have to find the pooled proportion. P hat is the total number of successes divided by the total sample sizes, right? And so it's x1 plus x2, which is nice because I actually have those number of successes. Otherwise, you'd have to calculate the number of successes over n1 plus n2. So in this case, it's 986 and 923. What do I have to do? If I'm going to use x1 and x2, then I should probably define what group 1 is and what group 2 is. So on the side here, I'm going to say let group 1 be the men or males. I can't remember, men and women. Doesn't matter. They all mean the same thing. Group 2 is the women. Okay. So what we could have here is this is the same as, whoa, it's a little jumpy. X for the men plus X for the women divided by N for the men plus N for the women, right? So we could have that, or you can define the groups here. Either way, we end up at, now I lost the numbers, 986 and 923. Oops. 986 plus 923 divided by 2253 plus 2629, I want to say. Okay, I think I got it. 986 plus 923 is 1909 over 2253 plus 2629, 4882. $19.09 divided by that is roughly 0.3910282671. For proportions, I'm going to keep 3 or 4 decimal places. In this case, keeping 4 decimal places is essentially the same as keeping 3, so I'm just going to lob it off at 3. I guess I could claim to 4 decimal places if I wanted to. Did I say roughly? In a weird way. I'm not even paying attention to myself. Oh, because it's so long, maybe. Hey, it's an approximation. This is exact, but I don't want to deal with this exact value. So it's approximately this. Anyways, proper. So now that I have this pooled proportion, right? So I need to first find the pooled proportion. Now I can use it to check the assumptions. And so now I can check that N1 times P hat is 22. And you know what? I'm going to get proper here. I'm going to try my best. 2253 times 0.391. 2253 times 0.391 is, and you're allowed decimal places in this case, 880.923, which is more than 10. So we're off to a good start. And then we're going to check the proportion of failures, right? So Q hat, which is going to be NM times Q hat, which is 2253 times 1 minus 0.391, which is 0.609 times 2253, I'm getting 1372.077, which is also more than 10, so it checks out. Now we do the same thing for the group of women, and so NW times P hat 2629 times 0.391. You can see how it's always going to work out, right? The conditions are always going to work. And if there is something that makes you say, hey, it doesn't say it was randomly selected, then what do? Then you have to say, I'm assuming the sample was randomly selected. Because if you tell me that these conditions do not check out at any point, then you shouldn't do the question, right? So then proceeding to do the question would be a huge mistake. So then I'd have to take marks off, right? But these conditions are always going to check out. We just have to show that they do, right, every time. So 2629 times 0.391 is 1027.939, which is, of course, more than 10. And NW times Q hat is 2629 times 0.609, which is 1601061, which is, of course, more than 10. Dink. Notice that when you add these up, you should get to 2629, right? Because you can either be a success or you can be a failure. In this case, success is living at your parents' house. Failure is not. Kind of a funny idea. Hey, plus 1027.939. So when I add these up, I do get to 2629, which is, of course, that makes sense, right? Because here I've taken 0.391 of the 2629, and then I have the rest here in the failures, right? So these are the expected number of successes and failures in each group. Okay, so now that was for the hypothesis test, whoops, right? Let's do it for the confidence interval. So now we're just checking the number of successes and the number of failures. And so for the confidence interval, it's a little bit easier. I need to check that, and because I have X1 and X2, right, that makes it even quicker. So I need to check that the X for the men, which was 986, which is more than 10, so that checks out. NM minus XM is 2253 minus 986 is 2253 minus 986 is 1267, which is also more than 10, just as we expected. So we have at least 10 successes and 10 failures in the male sample. Now we do the same for the women. So X women is 923. 923 is also greater than 10, so that checks out. And N women minus X women is 2629 minus 923, which is 1706, whoops, which is more than 10. Therefore, all conditions are satisfied, right? Or the conditions for inference are satisfied. Therefore, all conditions for inference. Inference is an umbrella term for hypothesis testing and confidence intervals, right? It's where we take information from a sample to learn about the population. So all conditions for inference are satisfied. Okay. Okay, now we can answer these questions. And what I'm going to do is, I can't remember if I had, okay, nice. So let's do part A. A is like to get you started. It's not a real question, but we'll answer it anyways. How large is the difference between the proportions of young men and young women who live with their parents? So now what we're going to need is we need to find P hat men minus P hat for the women. For the men, it was 986 divided by 2253 minus 923 divided by 2629, right? This is also where we're going to get our P hat for the men, and this is our P hat for the women. Okay. So once we do this and we find this difference, I'm going to do approximations for each of these. So 986 divided by 2253, I get approximately, favorite thing, approximately 0.437638704 minus 923, oops, divided by 2629, approximately 0.351084064. I'm going to round these, but I'm going to round to 4 decimal places because I want to capture a lot of as much of this activity as I can, right? And so you don't want to round until the very, very end, right? Especially, well, for part A, we're near the end here, so that's fine. But you can use rounded values, but use maybe round to 4 decimal places. All right, just remember, you want to try to capture as much of the activity as you can. So you could have just as easily just found these sample proportions. In this case, it looks like, nope, you have to round this one. Yeah. But let's see here. Oh yeah, so usually what I would do is I would find each of the sample proportions just kind of on their own, and then I would plug it in. But here, I guess I got lazy or excited, and I just decided to do the calculation in here. That's totally fine, right? But just as long as you keep in mind where those sample proportions are later when we need them. So then here, what I'm going to do is I'm going to have 0.4376 minus 0.3511. And this is approximately equal to, and I am obsessed because that's not true. Even here, it's approximately equal to. So let's get real, Emily. There. So if I do 0.4376 minus 0.3511, then I have a difference, whoops, of 0.0865. The question is going to be, right? We see that the proportion of males who live at home is slightly higher than the proportion of females in the sample, right? But what we're trying to figure out is there a significant difference, right? A statistically significant difference between these two groups, between these two proportions. And so that translates to, is 0.0865 significantly different from 0, right? There's going to be some wiggle room, right? Where, for example, right, if I ask you, am I holding my hands together? Yes, right? Then they're exactly the same right here. Exactly the same. Am I holding my hands together here? Sure, right? Am I holding my hands together here? I guess, right? And then it's not until a certain point where you say, I don't think you're holding your hands together. It looks like you're holding your ears or something, right? And so, so that's the idea. We allow some wiggle room where we say, okay, yeah, that's together, that's together, that's together. And then at some point we have this threshold where we say, looks like your hands aren't held together anymore, right? They're kind of just held up, right? That's the same idea. So what we're finding here, we want to know is this significantly different from 0? Significantly different from 0. Right, that's our question. So let's get to work. So now we found our sample proportions. So now we're ready to do the hypothesis test. And of course, I've been blabbing, but it's all important. Okay. So step 1 is to state our hypotheses. We've already read the question, right? So is there evidence that there's a significant difference? This is what tells me that I need a 2-sided test. Is there a difference here in the proportion of men who live in their parents' homes compared to women? So here we go. Step 1, and my page is all there, is to state the hypotheses. So in this case, H0 is that the proportion of men is equal to the proportion of women, right? Or PM minus PW is equal to 0. I'm so hung up on this one here, but you can use whichever one you want. So the alternative hypothesis is that the proportion of men is not equal to the proportion of women, or the proportion of men minus the proportion of women is not equal to 0, right? This second version highlights that we're comparing the difference to 0, right? So that's probably what I should be using, but I like these and they're easier to read, I think. Yeah. And so here, this is what makes it a 2-sided test, which means we need a 2-sided hypothesis or p-value later, p-value in step 3. Step 2, do the test. Z is P1 hat, PM hat minus PW hat divided by the square root of P hat Q hat times 1 over NW plus 1 over N. Oh, sorry, I didn't mean W, I meant M. There. We've already found this difference here. So in the interest of time, I'm going to say that this was 0.0865 from part A. And I also know that P hat was what, 0.391. From assumptions. And Q hat was 0.601, I want to say. Okay, so plugging those in, I get 0.0865, technically minus 0, right? If you wanted to remind yourself, right, you could do minus 0 here, but it doesn't really do anything. So I'm not going to include it because it's not on your formula sheet, and I don't want anyone to get confused. 0.391 times 0.601 times 1 over 2253 plus 1 over 2629. Scrunching it up a bit because I've got a page break. Being really careful with your calculations, but also I'm running out of time here, so I'm just going to go for it. 1 over, I focus on dealing with these fractions first and adding those up, and then I can multiply. Oh, perfect. It looks like I'm going to get to 0.609, but let me see here. 1 divided by 2253 plus bracket 1 divided by 2629 and bracket times 0.601 times 0.391. Make sure that you take the square root because otherwise it's going to make a mess. So I'll have that here, 0.865 divided by the square root of 0.00019. I've got scientific notation, so 1, 2, 3, 4, yeah, 1936855. It keeps going, but oh wow, you gave me the final answer. Holy smokes. So that's 0.0865 divided by 0.0139170959. 0.0865 divided by that. Unless I slipped up somewhere along the way, I'm getting 6.215. Oh, uh-oh. Uh-oh. I did screw up big time. 609. Here we go again. Sorry, I didn't catch that. This is 609. 609. Okay. Might change some things here. So much for me zipping ahead. That's not going to happen. Okay. 1 divided by 2253 plus 1 divided by 2629. Make sure you use brackets. Times 0.609 times 0.391. I tried to screw that up again. So now I have 0.001962637. Square root that. Okay, 0.01400941574, just so you can check your work. All right, now 0.0865 divided by that. Pretty similar, but I get 6.174418084. Now, what I'm going to do is I'm going to pause this recording and I'm going to finish the rest of the example. And I encourage you to do the same and then just watch it so that we can wrap up this section. But you can try it and check against the notes, but the remainder of the video will go through. But I know I'm all out of time. So I'll pause this here and then I'll pick up because okay. I'm back and we're going to finish this example. Okay, so we've got this relatively large z-score. And so now if I round this to 2 decimal places, because our z table can only handle 2 decimal places, we're going to be off the table anyways. We know that because we know it kind of ends at 3.49. It keeps going, but anything beyond 3.49, the area in the tail is so small that it doesn't matter. So we stopped showing it, but 6.17 to 2 decimal places. So now, oops, that doesn't look like. In step 3, we're going to find the p-value. So finding the p-value here, we look at our Z. This is our calculated Z, 6.17. And if we look at Z, which is centered on 0, I get a Z calculated, let's put it here, is 6.17, which means that this area is really, really small, right? From the Z table, we can see that, and if you want, it might be easier to look at the negative Z calculated, which is negative 6.17, because this is also the one-sided p-value, but then we want to have both sides because we had a two-sided test, right? And so here, we need the two-sided p-value. Okay, good. So using the Z table, we can go to the table, and here, that's old. If we go on the negative side, and let me just remove that there. If we go on the negative side, we have negative 3.49 is kind of where it maxes out. And so here, negative 3.49 can copy this and bring it in. So we can say using the Z table, we know the one-sided p-value is less than this 0.0002, right? We've worked enough with the Z table that we should feel pretty comfortable with jumping there. So we can say using the Z table, we find the area to the left of Z equal to negative 3.49 is 0.0002. So the area to the left of Z equal to negative 6.19, right? And so that's just the negative side of our calculated Z is less than 0.002, which means our two-sided p-value is less than 0.002 times 2, which means our two-sided p-value is less than 0.0002 times 2, which is 0.0004. And so that's what I'm going to use. I'm going to use the p-value that's less than 0.0004. In step 4 is our conclusion. Remember, we have 3 parts for the conclusion. You compare your p-value to your alpha level, right? 0.0004 is less than 0.05. It didn't give us a significance level. It didn't give us an alpha level to use. So we just use the default of 0.05. And so first thing I'm going to compare. So since the two-sided p-value is less than 0.0004, it is also less than the assumed alpha level, right? Because it's not given. So I'm going to call it the assumed alpha level. It is also less than the assumed alpha level of 0.05, right? Because it wasn't given. Which means if the P is low, in this case it is, right? It's less than 0.05, then we have enough evidence to reject H naught or something like that. So since the p-value is less than the alpha level, we have enough evidence. So I'll say which means we have enough evidence to reject H naught in favor of HA, right? If you're rejecting it, then you can say in favor of what? If you're not rejecting it, then that's the end, right? To reject H naught in favor of HA. Which means, right, what in terms of the question, I'm gonna, oh, I forgot I ditched the question. Let me grab it again here. Because I'm gonna want it for the next part anyways. So, which means now I'm just gonna reword the question as an answer. Okay. Which means, this means, the question was, is there evidence that there is a significant difference in the proportion of men who live in their parents' homes compared to women? Which means there is evidence, and then the exact same blurb again. So which means, so this means there is evidence that, oops, jumped in here, that there is a significant difference in the proportion of men, who, maybe I'll say young men, clarify, young men who live in their parents' homes. I'm sure you could phrase it a little bit better, but I usually just rephrase the question as an answer. So live in their parents' homes compared to young women. Whoops. Wait. Compared to young women. There. Notice, right? 3 parts. Compare the p-value to the alpha level. Okay. Then what does that mean in terms of the null hypothesis? So part 2, conclusion in terms of H naught. And then finally, answer the question. Answer the question. Which is really the conclusion in terms of the question. Conclusion in terms of the question. Okay. Note that the default alpha level if alpha level is not given, we assume alpha is 0.05. We've said that before, but it doesn't hurt to say it again. So now for part C, now we're going to make a 90% confidence interval for the difference in the proportion of men and women who live in their parents' homes. Remember, we've already checked the assumptions, so we don't need to worry about that. We can just go ahead, and they all checked out, so we're allowed to just go ahead and construct this confidence interval. So what we need is we need to set up our interval, and our interval, we had it before, it's on the formula sheet. And just as a reminder, right, here's the confidence interval for the difference in the proportions. I'm just going to bring this in on the side, but the more you use it, you're going to end up memorizing these things. And I know that probably feels impossible now. And then one day you're going to wake up and say, and say, hey, I remember all these formulas. But it's here, it's on the formula sheet if you need it, or your own personal made formula sheet if you are making one. Okay, so we need to set up, maybe I'll move this over. Why not just build on this here? So we have a lot of these components, right? We have this difference from part A, and so that's going to be 0.0865, I think it was. Let me check. Yeah. From part A. Z star. Now, Z star is going to depend on the confidence interval, right? And so, or the confidence level for a 90% confidence interval, then we need to look at the table, and we use the T table, right? Because at the bottom, right? So here I'm going to do a little, I don't know what, magic? No. A little cut and paste, a little copy pasta. Oops. There, close enough. Of course, these just keep going. Same thing here. And so if I want a 90% confidence interval, then my Z star is 1.645. And so here, my Z star is 1.645, and that's from here. All right. Now I have my P hat, I have my Q hat, or I might have to calculate my Q hat. I have my N1, I have my P2 hat, Q2 hat, N2 hat. So I'm going to have to plug those all in, but I have all the other components. So I have, let me remind myself, and let me just copy. Let me just copy this so I can grab these. I'm not going to keep these, but I just don't want to be scrolling up and down and forget every step of the way. So here, recall, we didn't calculate them explicitly, but PM hat is 986 over 2253, which is approximately 0.4376, and I didn't write that properly there. And PW hat was 923 over 2629, which was approximately 0.3511. Now I'm going to remove this because I'm just going to use the approximations. So that means that QM hat is 1 minus 0.4376, which is what? Turn my calculator on. 1 minus 0.4376 is 0.5624. And QW hat is 1 minus 0.3511. Puts me at 0.6489. So we don't need to introduce the pooled proportion for the confidence interval, but the pooled proportion actually makes the standard error a little bit easier to handle because now we have to use all these components here. And so we have PM hat minus PW hat plus minus Z star times the square root of PM hat QM hat over NM plus PW hat QW hat over NW. Kind of tricky to write it out with the subscripts. And if you had defined group 1 and group 2, you could use the 1, 2 subscripts. So we get 0.0865 plus minus 1.645 times the square root of, and this is when I use these values, 0.4376 times 0.5624 divided by 2253 plus 0.3511 times 0.6489 divided by 2629. Okay, this is a plus minus, right, to get that interval. Now I'm actually going to pause it here and I'm going to do these calculations because you don't need to watch me do it. I'll be right back. Okay, so now that I think about it, I should have double checked. So there's a chance that I slipped up on my calculator, but so if you're finding something different, then let me know. But I'll check it after just to make sure. But so I did so you have to multiply the numerator, divide by N1, which is 2253 in this case. So find that value, keep it somewhere safe, and then find this next value and then add them together and then take the square root. So you want to be really careful with order of operations here. Once you've taken the square root, you should have something like 0.01399, which you can then multiply by 1.645. This is your margin of error, right? So now you have your margin of error, 0.023, and I rounded it to 4 decimal places to match the 4 decimal places that I have for the difference estimate. So then I have to find the lower bound, so I have to take 0.0865 minus 0.0230, which puts me at 0.0635. And then I have to add 0.0230 to 0.0865, and that puts me at 0.1095. Once we have an interval, right, we have to interpret the interval. It's a little bit different because this is the difference in the proportions, right? And so if this difference is consistently larger than 0, which it is, right, what does that mean in terms of the proportion of men versus the proportion, or young men versus the proportion of young women? Well, it means that the proportion of young women is consistently less, right? Which is what we found, right? We found by our hypothesis test, we established, yes, there is a difference here. Now we're talking about, okay, well, what is that difference, right? And so let's see here. We are 90% confident the interval from 0.0635 to 0.1095 captures. Now notice it's the same setup as we had before, right? But now we're talking about captures the true difference in proportion, okay? And the question usually has something that you can use. Construct a 90% confidence interval for the difference in proportion of men and women who live in their parents' homes. So that's what I'm going to use, right? But it's talking about the difference in the proportion. So we're 95% confident that the interval from captures the true difference in proportion of men, or maybe I'll say young men. Oh, and I forgot the rest of the blurb. And young women who live in their parents' homes. And young women who live in their parents' homes. Okay, and as a kind of an add-on, right, we can say that this is the same as saying that we're 90% confident, or 90% confident that the interval from 6.35 to 10.95%, right? That's how many more men, right, live at home compared to the women, right? So alternatively, we are 95% confident that the interval, from 6.35% to 10.95%, because proportions are percentages, right? So if you want to talk about percentages, that's fine. We're 95% confident that the interval from 6.35 to 10.95 captures the true difference in proportions, or difference in percentages, which means that 6.35% up to 10.95% more males live at home, right? So 6.35% to 10.95% more males, or more young men, live at their parents' homes than young women, right? If you have a difference, then it's always one is more than the other, right? If there's a difference. Okay, so you could think about it that way, but in terms of the interpretation that I'm looking for, I'm just looking for this very straightforward interpretation, right? But then you might have to think about, okay, there might be a follow-up question that says, okay, so what does that mean in terms of how many more men live at home compared to the women? Okay, I think that answers that last question. It does. And so that concludes our 2 sample proportion section. So now we're ready to move on to some chi-squared tests next day. All right, see you next time.